Okay, it is 2 o'clock, so we're going to get started. Hi, my name is Lauren Tilton. I'm here with Taylor Arnold, and we're really excited to be here at useR to talk today about natural language processing. So to get us started, just to talk a little bit about our goals for today. Today, our goal is to introduce concepts and tools for doing exploratory and predictive modeling from textual sources. And we'll be focusing on natural language processing and specifically a package we developed called Clean NLP. So today we'll go over the core concepts of natural language processing, look at naive and non-naive approaches, strategies we have developed for doing NLP, particularly focusing on this Clean NLP package that we developed. And then we're going to primarily use English examples today from literature and from political science or from politics. But along the way, we're going to talk about how you can use other languages as well. And we decided to use English sources today to be the most approachable for all. So we're going to start again with some preliminary work about how we're going to be using R today and our approach to using it, as well as then talk about a naive approach to NLP through tokenizing text, as well as then look at how we approach the NLP pipeline using Clean NLP, and then look at modeling textual data, particularly for the statisticians in here, always the fun part. And then we'll look at some conclusions as well at the end to sum everything up. So just to tell you a little bit about ourselves, we're a bit of an eclectic team. I am actually a historian by training. I am a scholar of 20th century US culture, but I'm trained in the computational humanities or digital humanities, an emerging field across the United States and Europe. And in fact, there's a growing community of us who actually work just in R. So if you were to go to something like the programming historian, you will see that there's a whole group of us who are working about how can we actually use the R programming language to do computational work in the humanities. I'm hoping we're increasing our presence here at useR over the time to come. And as well, as I said, really what we mean when I say digital humanities is this is computational techniques to answer humanities questions. In other words, how can we analyze 100,000 books? How can I look at an entire run of speeches by a set of all the US presidents? How can we begin to do this analysis at scale? So in the way that scale has begun to impact other fields, those same sets of questions are actually making themselves their way into the humanities as well. And that is where I come in this kind of work. And I'll turn over to Taylor to speak about his work.
So I'm the statistician of our pair. So I work on the computational challenges and exploratory data analysis as it pertains to text and image processing. So today we're going to talk about the text processing, but I also do a lot of image work. And so what Lauren and I do is we partner a lot to kind of take the cutting edge things that are happening in text and image processing and apply them to questions that are of interest in the humanities and social sciences. So we have done a lot of joint work together. So we have our book, Humanities Data in R, that Lauren brought some copies along, and we haven't figured out how we're going to give them away yet, but we will give away a few of them in the second half of this session. And then there are two public projects that we have that we'd love you to check out if you're interested. There's Photogrammer at photogrammer.org, which is a digital project which charts a set of historical photographs in the US from 1935 to 1945. And then a new project that we have called Distant TV that applies computational techniques to the study of television. So it's really great to sit in my office and have all of the Bewitched episodes and all of the I Love Lucy episodes and call it work. So that's really fun to do. So for the tutorial today, if you'd like to follow along, it's a really big group, so like larger than sort of a real hands-on tutorial, but we do have all of the code and everything so you can completely replicate what we're doing today, all of the code, so you can go back home, you can follow along today, and you can go back home and look at the code as well and email us with questions. So if you'd like to do that, the way to do so is to clone the GitHub repository there. I'll pause with this slide a little bit. I know the internet connection is pretty slow in here. If you have trouble with it, I can at least airdrop it to you at the break if you have a Mac. Sorry? Oh, okay, thanks. It's github.com/statsmaths, both of them are plural, /useR with a capital R, 2017 underscore NLP. There's a period there, but that's not part of the link. So if you go there and you just clone the entire repository, you will get all of our notes for today. And the format of those notes are essentially or actually I already have them open. They are R Markdown files. So if you open them in RStudio, you can actually run each of the little code snippets and see what we're doing. And then it is these exact code snippets that constructed all of the slide decks that we have. So there's a mirror one-to-one so you can follow along. And we have a few bits where we'll ask you to modify it and change what we're going through. So there we go. So yeah, so that's the repository. So GitHub, stats, maths, and then useR 2017 underscore NLP. If you just, if the last bit is having trouble with you, you can go to my user page, and it's the last repository that I updated was the useR 2017. So just a note about the coding style. So there are many different ways to do things in R. Because it makes code for the way that we're processing text really clean and easy to work with, we're actually using kind of the tidyverse set of tools. You don't have to be an expert on them to follow what we're doing, but I just wanted to mention that if you're not as familiar with dplyr or ggplot2, they're going to show up in our little code snippets, and gritter pipes as well. So we'll try to explain what they're doing. What's really nice about the dplyr verbs is that they map onto database functions, and so if you're familiar with databases, they'll make sense. And the verbs are very descriptive. So what you think a verb that called filter does, it does something close to what something that would called filter would do. So the one that I did want to show, just because if you haven't seen them, it can be really confusing, and I didn't want to lose. Sorry, we're like a foot apart, so this is going to be hard. So the pipes, so pipes are a way of sending one output of R into the first argument of the next function in R. So the pipe is this %, arrow, %. So I know a lot of you have seen it, but I just wanted to show an example if someone is unfamiliar with them. So if I have the sequence of numbers 1 through 10 and I pipe it to the function length, what happens is this is the same as calling the function length on the sequence from 1 to 10, and it spits out that the length of this thing is 10. And similarly, if I take a matrix of the integers from 1 to 12, and I make that matrix have 4 columns, it should then have 3 rows, and if I pipe it to the dimension function, it will tell me that it's a 3 by 4 matrix. So you'll see that all of the text and image, or all of the text processing that we're doing today is we're going to build up these pipes of increasingly complex commands. And then as we change 1 or 2 things, we'll change the type of analysis that we're doing. So this piping structure is really predominant in the code that we're doing today. And so the package that sort of plays really nicely with pipes and dplyr and ggplot2 and readr and all the other tidyverse is the package that we've been writing called clean NLP. And so the idea here, as we will describe throughout the tutorial, is to go from raw text to a data frame that prescribes to all of the tidy data principles so that we can do things like plotting and modeling and exploratory analysis. And we will explain sort of from the simplest uses to its most complex uses in this tutorial. So in order to follow along with the slides, you'll just need to download this. It's available on CRAN. If you're interested in more of the internals of the package, which we won't be covering in this tutorial, we're just going to cover like how do you use it. If you're interested in how it's actually built and why it's built the way that it's built, there's a paper that's up on the R Journal that's will be published in the next issue of the R Journal that you can see. There it's also linked from the CRAN page, and I'm also giving a talk tomorrow at 2:06 describing more of the internals of the package if after this you're interested in hearing more about it. Okay. So as Lauren said, the talk is really broken up into these 3 different topics. I like to organize things like a lot. My desk is really tidy. My files are really tidy. So my data is really tidy. So everything's really tidy. So we broke the talk up into 3 little slide decks so that it's easier to find something when you go back. I hate having a slide deck with 200 slides in it. So we're just going to start with the first one. So where is that here? Okay. So the start of every slide deck, and as I said, these are all R Markdown files, and so if you download them, you can run them. So the first slide on every one is just all of the packages you would need to read to run the rest of the code. So I just put it up here so it's easy when you're replicating it. You don't have to constantly say, oh, I forgot this package, I forgot that one. So these are all the packages that we need to install for it. I assume most of you have a lot of them, but cleanNLP is the particular one that refers to text processing that we need here. So tokenization. So as Lauren was saying, we're mostly going to work with English text because it's really the only language that I know very well. But I did want to show you how all of these principles apply to other languages as well, other natural languages. So here is a short snippet of text from Albertus Camus's L'étranger, or the stranger, or the outsider, depending on how it gets translated into English. So this is just the opening few lines. And so tokenization, so what would we do if we wanted to work with this set of text, right? So I use stringy wrap here just to print it out on the slide. But really the way that this is stored in R is just one big long string. So what can I do with this one big long string? Well, I can't really do much with it, right? It's just a set of characters. I can't figure out how many words there are very easily. I can't figure out how many sentences there are. I can't figure out what tense he's talking in. I can't really do anything with this text as just a pure string. I need to somehow capture the semantic meaning of these words in R. And the most straightforward way to do this, the simplest one, is to split it into what we call tokens, to split apart the words and punctuation marks into their own elements of a vector. And you can think, well, oh, that's not that hard, and it really isn't that hard. So the most natural way of doing that would be to just split on white space. So to say, split this token wherever I see a space and break it apart, right? So when I do that, it works reasonably well, right? You can see here. So I'm just saying, create a new element of this vector whenever there's a white space. You can see maman becomes a word, est becomes a word, mort, we, er, all of these things. They become words, but there are some errors, right? So for example, the first word aujourd'hui, so yesterday in French, it's followed by a comma, and the comma actually becomes part of the word yesterday, even though it should actually be its own token. It's a punctuation mark. It's not part of the word today. And you can see why that happened, because there's no space between today and the comma. So what do we actually want to do? We want to split using the cleanNLP package. And so there are many packages in R that will do tokenization. So one of them is tokenizers, one of them is tidytext. There are a few others that do a really good job of tokenizing text. The reason we're going to use cleanNLP here is because cleanNLP is set up to, with just a few changes that we'll show in the next deck of slides, allow us to add additional things that go far beyond tokenization, like part-of-speech tagging, dependency tagging, co-reference tagging, all of those things. So I'm going to show you how to do this in cleanNLP. So tokenizing text is pretty straightforward. We read in the cleanNLP package, so just by calling the library command. And then I have to initialize a backend. So I'm not going to explain what backends are right now, because we're just going to use the tokenizers backend. The next set of slides will actually show what are the different choices and why might you choose the different backends that are available. So here I'm just going to say, okay, we have to initialize something. We have to tell the internal cleanNLP engine that we want to do tokenization. So I will run the init tokenizers function, and I will pass it the locale of the text. Now, here I'm going to say, since this is French text, that I'm going to set the locale to French. In practice, if you're working with Western languages, they essentially use the Latin alphabet. It doesn't really matter. It probably wouldn't change it if I did English or Spanish or German. But I'll just do it for French because this is French text. But it would matter if I was, say, parsing Japanese text. I would have to make the locale equal to Japanese or Korean or Chinese. Okay, so once I've initialized the backend, that happens almost instantaneously. Then we have this function in cleanNLP called run annotators. So run annotators actually does the process, in this case, of tokenization, of taking the string and splitting it into its constituent parts. But it's doing it, it's using a much more complicated set of rules that takes care of punctuation marks, commas, quotation marks, periods, all of those different things. And so I run the run annotators on the string L'étranger, which contains the text that I'm working with. And then I have this option at the end, as_strings. So I have to tell it, I'm actually telling R, I am passing you the literal text that I want to work with. The alternative would be as_strings equals false, where instead I'm passing a vector of the paths to the texts. The benefit of the latter one is that you do not have to read all of the text into memory. So like I said, I work with really large data sets. They don't always all fit in memory. So this was built with that in mind. So you can pass it pointers to the files that you want to read in rather than the files themselves. So once we run that, and again, this is just tokenization, and it's a very short text, so this happens almost instantaneously. The object that gets returned is a clean NLP object. So it spits out this thing at the bottom. It just says, I am a clean NLP object, an annotation object, and I have just one document because there was just one string in here. In a moment, the examples that we're really working through will have far more documents in them. But right now, we just have one. So this object, this annotation object, seems like it's really complicated. I know there are some R packages, and oftentimes for very good reasons, where they construct complex objects, and then they have all these different functions that act on them, and you have to understand this whole different grammar just for working with this new object. The annotation object is not like that at all. It's just a list of data frames. So the idea is that I actually want to return, in database theory, like a whole database, so a collection of tables. And there's not a really nice way that I know of, at least in R, to do that. So I return a list of data frames. The talk that I give tomorrow will be about why is it set up that way, what's the benefit of all of these different data frames. It turns out that there's a nice normalized database, which has really great properties from database theory. But to simplify things today, and when I teach this, and when I do a lot of work on this as well, I don't want to work with that normalized database. It's kind of too pretty and clean. I actually just want one data frame to work on. I don't want to worry about all of the different keys and how to relate them and how to work with them. So we're going to call this function getCombine, which takes all of those tables and denormalizes them into one just data frame. And so the object that comes out of getCombine is just a data frame. So everything else that we're going to do on this object, it doesn't require anything particular from the clean NLP package, which is really nice. So we can just use it. We can plot it in ggplot2. We can pipe it through the dplyr verbs. We can do whatever. We can save it with read.csv or read_csv. So we can work with it just as if it's a regular data frame. And so that's the theme sort of here today, is that we want to take the text and get it into a format that we're familiar with as fast as possible, so that we can use all the tools in R that are built to work with data frames rather than having to reinvent them all for text. But why am I not just going to stop here and say we're done? Well, the things we want to do with text are not always the same things we'd want to do not with text. So a lot of what we're going to describe is what's in this output object and why are they useful. So the data frame that comes out of this has one row per token. So remember, I wanted to take my text and split it into words and punctuation marks. So now I've done that by each row of this data frame contains one of those tokens. And if we were to, on a slide, I can't fit them all, but if you did it on your own in RStudio, you could read all of the words down the column, and it would essentially reconstruct the original text. There are some other keys on here that we will use. ID just tells me that these all come from the first document. So ID, whenever you see ID in these notes, think the document ID. I wanted to call it the DID, but then I kept seeing the word did, and I didn't like that, so I made it ID instead. SID tells me what the sentence number is within the document, and then TID tells me the token ID, the token number inside of the document. So these are the keys that define that particular row. If you're familiar with like how a database works, the three of those together form a key for this row of the database or the data set. The next row just tells me the word that that token actually represents. CID tells me the offset in characters into the original text, which at first I didn't think was very useful, but can be really useful if you want to reconstruct the text later on. And then similarly, spaces tells me how much white space there was following that token. So you can see aujourd'hui, there was no white space before the comma, so spaces is equal to 0. All of the other tokens have a space after them, so space is equal to 1. And then just to pick off just the word column, so that you can believe me that this did the right thing essentially everywhere. So it did correctly tokenize the text for the most part, so it actually got those punctuation marks parsed off. It has the French quotes. So that's like a quote mark in French, the semicolons and all of that. The only things that don't get tokenized that a more fancy tokenizer would do, that we'll see in the next set of slides, is these conjunctions. So j'ai is a conjunction of je, I, and a, which is to have. So I have, a fancier tokenizer would actually split that into 2 tokens because it's a conjunction of 2 separate tokens, but that's asking a little too much of the simple tokenizer. And the same thing of the aisle here, l'asile. And then, do you want me to do this? Yeah. So then, that's so that for this one particular little piece of French. We actually want to do this same sort of tokenization on a much bigger data set that's going to be interesting and carry us through the next set of slides. Actually, the whole next two versions, we're going to work with a data set that consists of the 56 short stories that Sir Arthur Conan Doyle wrote about Sherlock Holmes. So we like him because it's out of copyright, which is fantastic. I know the historian always reminds me of what's in copyright and what's out of copyright in the US. They're also pretty short, so they're all included in the GitHub repository, so you have the raw text. And because it's not under copyright, I can freely distribute them, but there are enough to see some interesting patterns over the course of this character development through the 56 stories. So what I need to do is I'm just going to create a little metadata table that contains one row for each story. This will just be nice to join into the data that I create so that we have all the names of the stories attached to the actual things that we know about them. So I'm just calling the dir command here to get the list of where all of these things live inside of the repository. Then I'm creating a data frame, which just, I'm giving them the ID numbers 1 through 56, and then stripping off the .txt at the end and the number at the beginning, and giving it the name. So the first name of the story is A Scandal in Bohemia. So we'll look a bit at that one. So how can we use clean NLP? Just more as a review, we actually have to do nothing really all that different. If I want to annotate this set in clean NLP, I read in the clean NLP package. I initialize the tokenizer's backend here. Just to be pedantic, I'm going to use Great British English. I'll set the locale. Again, it wouldn't probably affect anything in this case, but I will just do it since it is British text. And then I will run the annotators over the paths. So these are paths. They're URIs to where the files live. I don't have to set the as strings because I'm just saying this is where the text lives. I didn't actually want to read it in for you. R will do that underneath the hood, and it will sort of read one story in at a time and be very memory efficient about it. And then at the end, I get a sort of this clean NLP object that I don't want to work with today. It's a little harder to work with that one. So I'll call get combine and get a data frame out, this sh_tokens. And it essentially looks the same as the data frame we had before. One row per token, an ID, an SID, a TID, map back into the original text, and the number of spaces following it. But you can see here now this data set's much bigger, so it has 550,000 rows to it. So there are 550,000 tokens, so words and punctuation marks in the short stories. And if we look at just a particular sentence, I can call off, here's the 10th sentence in the corpus of the first document. So this is the Scandal in Bohemia, the 10th sentence in it. And we can just see printed out the first 12 rows of it. And you can read down the line of words what this means. So grit in a sensitive instrument, comma, or a crack in one of. And so that's the beginning of the 10th sentence in this story. So if you're working on this on your own, I know the internet's a bit hard here, so it might be hard to actually get to get all of the data downloaded. But you can pick a few other sentences and see whether or not they tokenized correctly. And what you'll find if you look at enough of them is that there are some errors still. So one error that we know of that we will fix in just a little bit is that if there's something like Mr. Holmes, Mr. period, it will incorrectly think that the abbreviation Mr. is the end of a sentence. So this works pretty well, but just keep in the back of your head that everything we're doing here, from here on through the end of this slide deck, is really an approximation. It's pretty good, it works fairly well, but it has some errors in it. So if you look through enough of them, you'll find these. Yeah.
So we're going to fix some of those errors in a little bit, but before we do that, talk a little bit about why we might start doing this, and I'm just going to step on my tippy toes here. So we're going to look a little bit at what these tokens might be able to start telling us about style. So we can begin by doing that by trying to figure out some patterns we might want to begin to look at. So the examples include maybe we want to look at the lengths of sentences. So do some authors write longer sentences, some shorter? Do some newspapers write longer sentences, shorter? Are Fox News' sentences short? Are New York Times long, right? We could think about how these might tell us something about style in different genres. Also, we can begin to look at number of citations. presence of known characters, so who are the main people that are being spoken about, as well as maybe hashtags in a tweet. We can search by those, as well as look at, say, something like the ratio of quotes and dialogue. So how many often are people quoting different primary sources versus maybe synthesizing them in their own words, right? How that might tell us about different styles of writing or how people cover or the rhetorical devices they're using, say, either in different fields or areas. So one of the first things we're going to look at is how often Watson homes occur within each text. And so we're going to then just plot that on our using ggplot, and we can actually begin to just see all of the stories that were written and where each of the characters is mentioned. And we can actually begin to see patterns. So we see that Watson and Holmes are mentioned kind of early on. We see a gap around stories 16, 17, 18, 19, 20, right in there. And then they start to get mentioned a lot more prominently again. And then you'll see this line that we've pointed out here. Basically, Sherlock Holmes and Watson are not mentioned at all until the last third of the story. And that was actually meant to be the last short story he wrote. And then actually he was pressed, Arthur Joy was pressed to keep writing. So we can actually see how he started to make a narrative change and then actually kept going as well. And so these kind of patterns, at least for humanities or literary scholars, like why are these shifts? Why do the characters drop out in certain parts of the story? Why do they no longer get mentioned? And you could think about that in maybe how newspapers cover stories. Why do certain people get mentioned or dropped out of how we talk about, say, world events, or how we frame different kinds of people, or how certain places or whatnot get mentioned or don't get mentioned? You can start to see how that can get extended across. You could do this to Twitter or other areas. And so we can actually begin to start to ask questions about these patterns that we see, just using just recognizing names for starters. Another way is to look at the average sentence length. So here, we're just going to count the number of periods, question marks, and exclamation marks. Now, right now, the way we're doing it requires that I, as an English speaker, know that these are the ways that sentences end, right? We're going to show you in a little bit techniques where the NLP package already knows and has already been trained to recognize where sentences end. But right now, I, as just a English speaker, note generally an exclamation mark, right? A period, a question mark are ways that people end their sentences, and we can use that to look at sentence length across these stories. So we can start to see patterns about how they kind of vary a bit. This is kind of exciting. For example, I have a friend who's a scholar who's trying to figure out the anatomy of a bestseller. Can we look at the sentence lengths of an entire run of best-selling books to see if they start to have patterns like this that might tell publishers how they might work with authors to establish, look at stylistic components that make for bestsellers, right? Can we start to see these sort of patterns throughout? This might be one of the simplest ones, but you can extrapolate up from there. And so we see a little bit of shifts across. Starts with sort of longer, starts with this first story very short, gets a little bit longer, and drops off toward the end as well. So we can start to see a little bit about his style there as well. And so I think I'll turn it over. Oh, yeah, okay. So then another one we're going to look at is looking at which tokens might be interesting to identify and tabulate. In other words, what terms might start to give us some ideas about the major themes or ideas that are in these stories, right? Assume you know nothing about Sherlock Holmes. How many people are familiar with Sherlock Holmes? Raise your hands. Okay, a fair amount, right? But some are not. So let's say you know nothing about him and what's going on. Well, what we can actually then begin to do is look at some of the most common terms across the corpus to try to get an idea. So let's just do a count, right, of the most common tokens. Commas, periods, not very exciting, right? There's a lot of those. That doesn't really tell me anything super interesting, at least not yet. So what can we do next? Well, we can look a little bit further and start to get rid of that punctuation, look a little bit further, and look down and see. When we get to I, to, of, and, these are very, very common terms in the English language. Again, not the most semantically meaningful So what we want to actually do is develop a stop words list. So we want a list of words that have been determined that say, these are so common that they don't really always give me as much insight into what the major themes or topics are of this text. How can I dig a little bit deeper? And so we can actually then, built in is a stop words list for different languages. In this case, you can just see the top 25 in the English stop words list. One of the keys here is you can either make your own stop words list or use ones out of the box. But we always say to check your stop words list and see if there's words that might be really interesting. So I might be interested in, say, the years, about how time is spoken about in this text. I may actually want to keep year and not have it get thrown out. So a little bit about what is your object of study and what are you trying to learn about the text. So adjusting those stop words lists can be a big part of that. The other part I like to use is that, for example, I've done text natural language processing on the entire 40-year run of American Quarterly. That is the major scholarly magazine in my field of American studies. I want to throw out America, United States, right? These type of terms become no longer meaningful because they get used so often. So you also can add those terms accordingly for your needs. And so what we can then begin to look at is actually then take the top 10 occurrences within each text. And what we've done is, because it's just reading the text, we've done a left join to add that metadata back in so that I know which story I'm talking about and which year that story is in order to give some more of that information. And what we can then do is say, look at A Scandal in Bohemia and see what the biggest themes are. Or let's start to get a sense of some of the main terms. And so we can see here Holmes, photograph, king, majesty, little, Adler. Does anyone remember what A Scandal in Bohemia is about? Okay, it's been a while, huh? So we get a sense, though. We get a little bit of a sense. And this is his first story. So basically, the king, His Majesty, has hired Holmes, Sherlock, to find his photograph that Miss Adler has taken. It's a very scandalous photograph. And he needs that photograph back with Miss Adler. It's not quite as exciting as one thinks. Just remember, it's a little bit earlier literature. But he needs that photograph back. And so we start to get a little bit of sense of some of the terms here that start to give us a sense of what this story might be about. This can be really helpful too if you have a huge corpus and you're just trying to get a sense really quickly of what you're looking at. For example, Twitter data is a really good example of that. You're pulling a huge body of literature. What are people talking about? Trying to get an idea of what in the world people are kind of navigating around, and starts to give you some hints about maybe some areas that, one, you may have known to look at, or some topics or themes you may not have thought were even a part of that conversation. You can imagine that for blogs, if you're pulling Tumblr or other areas, that you might start to see some themes you hadn't seen before. And so we do this again for his last bow. We start to get a sense again. We've got von Bork, we've got Holmes, Americans, German, car, paper. So we get a little bit of sense, okay, there's something going on with some papers. It's about getting something safe, maybe. And so this story is about Holmes has been hired by his friend to find two characters who have gone missing. And we're going to find out a little bit more about who those characters are in a little bit. But quite now, this is a little bit more fuzzy exactly about what we're seeing, but we're starting to get a sense as well using these stop words. Let's see, and then, so if you would like, you can pick another story and start to get a feel for some of those characters or terms that you might be seeing. And then if you're exciting, there are really good summaries on Wikipedia if you're trying to sense about what you saw is actually the themes that we're seeing. But we're going to dig a little bit deeper into that in a little bit. So we'll switch over.
And actually, this is a good time to pause, and if there are just any quick questions or thoughts or concerns. Yeah? Oh. So this particular data set came from Project Gutenberg, which publishes a lot of out-of-print texts. If you want to work with it and the way that it's all going on in here, they're actually included in that GitHub repository. No, so actually that, the pre-processing, so going from some messy data set to the clean text is kind of before you use clean NLP. We actually had that in the conclusions, but I probably should have put it in the intro as well. So the removing HTML tags, the extracting it from PDFs, that's not actually the goal of this package. It assumes that you have the text in a text file, and then you want to actually extract features from that text. So there are great packages for doing the other steps, but that's kind of out of scope of this one. When the data frame is too large? So what's nice about working with the data frames is that they are actually all stored during the annotation process. They are stored on disk. So what happens internally in the package is it reads in a little chunk of text, annotates it, writes it to disk, reads a little bit, annotates it. It's just by default, because what most people have when they first open up the package and want to use it is they have something small they want to play with. So by default, it reads it all into R at the end of the session. But there's an option actually to not do that. So you can actually work with gigabytes of data, and it will just deal with little chunks of it, and then you can go back through and read in little chunks of the data or grep it or do whatever you want with this very large file. So there's actually, as long as you change one of the function options in run annotators, it's completely memory bounded, which is really nice about it. Yeah. Uh-huh. Oh, the CID is it's the character ID, so it maps back to the character offset of that token in the original text. Yeah, so if you, and it's not so much my work, but some people are really concerned with like, where was this in the original text? It can matter a lot if you're dealing with like non-Western languages, like you want to know where was this particular character found as an offset. You can actually do that with the CID. So it's put at the end of the table because it essentially serves as a foreign key. It tells me how can I identify this back with the original text. So cool. And you can also use it to figure out how much white space there is in between all the different things. Okay, one more. Yep.
Yeah, how are the homes stored ordered so that handle is looking at them?
So they're ordered chronologically, and then in the order that they were published in the Strand magazine. So they were, the first few I think were just on their own, and then the rest were serialized as like a special issue of the Strand. So they're roughly in chronological order, and when they were all published at the same time, it was the order they came in that serialized volume. Yeah. Okay, so we'll have some more time for other questions later, but this is great. Keep them coming. Okay, so what Lauren was showing before was that we can use the fact that we know that Sherlock Holmes and John Watson are two characters that show up in all of these texts. We can use that to identify which tokens are Holmes, which ones are Watson, and figure out where Holmes and Watson are. And as Lauren was showing, that actually gives us a lot about what's going on in these texts. It tells us sort of what's the narrative arc. Holmes and Watson are generally involved with solving a crime. They're not involved in committing a crime. So if they're absent for a while, that's usually when something is happening that's not involved with solving the crime. The crime is ongoing or something is changing about the crime. So in this particular one, knowing where Watson and Holmes are is really useful. In a lot of examples, and actually as Lauren was showing for his last bow, there are other characters. We don't actually know who they are a priori, and we'd actually prefer to let the R and the package and the data tell us who the main characters are. And so this comes up all the time when we're working with text to figure out who are the characters in fiction or who are just the main players in nonfiction. And this tells us so much about what's going on in something. So if we see a bunch of social media tweets, if we're parsing Twitter data, we see the people that are being mentioned. We often know, are we talking about politics? Are we talking about movies? Are we talking about TV? Are we talking about music? And also just like, what are we actually talking about? If we see Kim Jong-un talked about, we know we're talking about something in Korea. If we see Trump mentioned, we know we're probably talking about US politics. So the people often tell us what's actually going on, what are the main themes and locations, and what are we talking about. And then obviously in fiction, the characters tell us sort of what's going on in the major plot arcs, and also if we can see how co-located characters are. If we see two characters mentioned or doing things very close to one another, they're probably acting with one another and they know one another. So if you think of, there's some really great studies of Shakespeare's plays where they look at a network analysis extracted from the text of which characters are on scene at the same time as one another. So seeing where the characters are really important for understanding what's going on in both fiction and nonfiction. So we can try to identify these using the tokens that we have. We don't have like part-of-speech tags, we don't have entities, we don't have any of these fancier things that would make this really easy yet, but we can do a pretty good job with just the tokens. And so the way that we can do that with just the tokens is we can take our data set, that data frame, and we can filter on whether or not the lowercase version of the word is a stop word, because we want to get rid of the stop words as before. But then we want to figure out, is the lowercase version of the word equal to itself? So essentially what I'm doing in this line here is I'm saying, does this word contain any capital letters? And why is that? Well, character names in English tend to have capital nouns. We capitalize proper nouns in English. And so this line here will, for the most part, pick out all the proper nouns. Now, we'll also get things that start sentences. So like my favorite thing is chocolate, like my, as at the beginning of the sentence. So it would also be picked up by this. But that's okay. I'll show why in a second. It's okay to get those occasional things that start sentences. But we can filter out the proper nouns here, because then I'm going to count them and figure out, grouped by the story, what are the top 10 most common things that are capitalized in that text. And so what it turns out to be, although we could actually do something kind of clever, we could see what words precede, follow a period or a question mark or an exclamation mark and sort of start the beginning of a sentence. For the most part, we're pretty safe with this because words that are not proper nouns that just occasionally come at the beginning, that form of the word is not going to occur very often, whereas homes is always capitalized. And so this is going to tend to pick out proper nouns. I actually think in the stories we looked at, it has no false positives. So we'll find the 10 most common proper nouns in each of the stories. So here is A Scandal in Bohemia again, and we see all of the proper nouns. So before, when we looked at the list, a lot of the top words that occurred when we get rid of the stop words were proper names, but it also contained things like photograph and shoe and table. And now we just have the proper nouns. So we have Holmes, King, Majesty, Adler, Irene, Briony Lodge actually is a location, Norton Street is a location. So we have some false positives in the sense that these are not all characters, but no false positives in the sense that these are all proper nouns. Well, street sort of is. Street is because it's coming in conjunction with Norton Street or Baker Street or something like that. And then similarly, we see in his last bow the character names that we were looking before. So von Bork, Martha Barron. Is Martha Barron the other one they're looking for? Yeah, Martha Barron's the other character that Sherlock Holmes is looking for. And we do see some proper nouns like German and Altamont and American that are obviously proper nouns, but they're not characters. And we'll see later on how we can fix that. But we're getting closer and closer. So what if we want to reconstruct that plot we did before with where is the top character, the most referenced character in the text? Where does it occur? But instead of just doing Watson and Holmes, we want to do for that story, where does the most important or the most mentioned character occur? We can do that by, again, as I mentioned, we have these long pipe things, but essentially, if you go from slide to slide, we're changing 1 or 2 lines at most and sort of really changing the analysis. So here, I'm going to take all of the tokens, I'm going to throw out things that are less than 4 characters long because those tend to be honorifics like Mr., Dr., Sir, etc. Then I'm going to throw out words that are equal to Sherlock Holmes or John Watson because most of the stories, they will turn up more than anyone else. You can see, for example, Scandal of Bohemia, Holmes would have been the most important character, but that's not interesting. We already know where he is. And then we again throw out stop words, and we just find the proper nouns. And then I find the most mentioned proper noun that was not Watson or Holmes. So we can redo, so we see here in the Scandal in Bohemia, it was Majesty, and in the Illustrious Client, it was Baron. So then when we have that top name there, it works generally pretty well. Sometimes we don't actually have like the last name or the first name, but we have the honorific. The reason actually for that is that it's just the way that Sherlock Holmes was written. If someone is the Colonel so-and-so, they were often referred to as just the Colonel. So Colonel shows up more than their actual name. A little bit of a change of English over time. So we can make use of a semi-join function. So I have this list of the top terms, and I just want to see, well, which of the tokens in my original data set match those top character terms when I compare them across stories and across words. And when I do that, I can replicate the plot we had before, and we can see the kind of narrative arc of where do these characters come into play. And so they're all over the board, but we definitely see different patterns. For the most part, these were released in sets of 5 or 6, and so you can see little clumps here like this set here. The main characters are often sort of starting, this one here, in episode 40, I actually forget which book that is. The main character is someone who's like setting off the plot, so it's a client who comes to Sherlock Holmes and has a case. But then some of the other ones where the main character shows up more at the end, that's probably because it's the main antagonist of the piece that Sherlock Holmes is after. So you get this sense of where the characters are and what their importance is. And so if you do this, and you have the data set in there, one thing that's interesting to do is to not remove Holmes or Watson, and to see how often they actually show up as the most important character. And what's interesting from those 2 examples that I showed you, sometimes Holmes is, sometimes Watson is, and sometimes someone else is. And you can actually get a sense in some way about what type of Sherlock Holmes story is if you've read all 56 of them, just by figuring out who is the most mentioned character. So if it's Holmes, it was probably one of these more action-based one where Holmes is out in, I don't know, doing cocaine and doing all of his crazy stuff. And actually solving the case actively, whereas if Watson was more of the main character, this is Watson telling, the ones where Watson is telling Holmes a story, and Holmes is kind of solving it and saying, you idiot, I knew, how did you not know what this was? And when it's someone else, it's one of these ones where there's a client and he's talking with Holmes a lot. So you can, if you really bifurcate them and look at them, especially if you're familiar with the Sherlock Holmes, you can see that this does a good job of breaking all the stories into 3 kind of major types of Sherlock Holmes stories. So identifying themes.
So now what we want to do is come back to looking at themes, but this time try to look at ones that are not the characters that we've been able to identify already. So what can we find out from them once we take out these proper nouns out of the equation? So what we can do is we just took our original code and modified it to only count all the lowercase letters, again, to take out our proper nouns. And so what we can then do is then filter them and start to see, again, some of the other terms in our themes in our short story. So you can see here a scandal in Bohemia again. We can see a little bit more about the photograph, the street, a woman, her hand, a door. We start to get a little bit of sense of some of the other details that are surrounding this story as well. And again, this is a Scandal in Bohemia is a short story, but if you were to do this at scale with a lot of other, like newspapers again, or Twitter data, you actually can start to see some of the other major themes as well that begin to come out of the text. I do this, for example, we do this on historical letters, for example. So if we start to pull out sort of the main, some of the main names, you can get seeing themes like, I look at a lot of U.S. culture, so lots of things about music or jazz or drums, or you start to see some of the instruments or something that people get really excited about, and you start to see some of the themes along other analytical lines besides just character names. And so we can see that here a little bit about the photograph. Again, she's hiding behind a door, so we start to see a little bit more of those pieces. So the stop words are great. They start to give us a little bit deeper dive, but there's another technique we want to talk about as well, and that is actually not working with stop words, but actually working with word frequency lists. So also what you can do here is instead of pulling out the stop words, we know what some of the most frequent terms are in English. They've been calculated here. And so that's included. And instead, what we can do is actually pull those out and decide what percentage of them do we want to pull out. So here's just a sort of the first 9, some of the most frequent terms. They map pretty well onto some of the stop words, like the, of, and, to, a. And so what we can then do is take these decide what percentage of them we want to remove, and then actually look at our stories again. And so when we do that, we get another set of words to look at a scandal in Bohemia. So we've actually, this is just a different technique. So stop words are using the word frequencies. And so in this case, we get a different set of themes. We get photograph, door, cried, eyes, looked, remarked. We get a sort of slightly different set of themes. And we like to do this to sort of do both sets of them against a corpus at any given time to see if different topics come out that may not have come out before, that you might see something you hadn't seen before. Again, with most of text analysis, there's no one right way to do it. There's multiple strategies for how to get more meaning out of the text or in different sort of, see different possibilities in it. And so this is one of the ways that we've also approached it, and you can actually go about doing this as well. And I think that is the end of this deck. So we are going to now move to our next set. Where do you have it on here? Here we go. Okay, you want to ask if there's any questions? Are there any questions?
Yeah, so those come from the missing tokens are spaces. So the tokenizer's backend is counting those spaces and giving them an ID. So a lot of times you'll see a missing TID because it refers to the space. So we've actually thought about whether or not we should renormalize it so that they start from 1 through whatever. But right now, the way it works, we just allow it to keep those IDs for the spaces and then remove the spaces when we don't want them internally. To be honest, the TID, all of the IDs, the way that I think of them is that they are just that. They're IDs, they're keys. They shouldn't really have any intrinsic meaning. So you shouldn't rely on token 7 being the 7th token. It's just a way of describing that particular row of the data frame. If you want to count how many tokens are in a particular sentence or document, you should actually do that, count the number of rows in the data set. But it's a good question, so that's why they're missing. And it actually, at the moment, depends on the way that you do the tokenization. But that's why they're there. Mm-hmm.
One question, you are talking about delivery time stream. How can you control that the time stream will lead to the correct results?
Sorry, what, can you?
You have talked about the delivery time stream, percentage and so on. And I would like to know how you can control that the time stream leads to the correct results.
So the technique of using the frequencies is an exploratory data analysis. So there's not a right answer. The point actually, what's really nice about using the frequency cutoff versus the stop words list is that the stop words list is a little too binary sometimes. Like a word is either in it or it's out of it. If I want to remove slightly more terms, I have to change the stop word list and figure out what they are. What's really nice about this is that while I'm doing exploratory analysis, I can just change the frequency cutoff and get different words. So sometimes I'll get the really rare terms that occur. Sometimes I'll get the fairly rare term. I can just play around with it and see what they look like. But it's not a right answer. I mean, the best use of that technique, it's actually, the way I think of it is that stop words, the downside of that technique is that there's no tuning parameter to play with, whereas this one has this tuning parameter, so I can look at it at different levels. And I find for every time I use it on a different corpus, there's different levels that show something interesting.
And you'll see on the last question that we set the frequency to 0.01%. We just played with that. So I would say just to play around with it. But this is where knowing your corpus does matter. This is having a little bit of idea of what you're looking at starts to really become a part of the equation.
Mm-hmm.
Mine's similar to that question, but for the frequency cutoff, if you were familiar with the corpus that you were looking for,
Uh-huh.
would you still use the frequency cutoff, or would you go back to using the stop words, or would you have like some set parameters each time?
No, I think if I wasn't familiar with it, I'd be even more inclined to use it. I'd start at 0.1, and then I'd start at 0.01, and then 0.001, and I would just see what comes out. So, like the best cutoff, it tends to depend on how specialized the text is. So Sherlock Holmes was mass audience fiction, so you can have a pretty high cutoff and get interesting results. If we're looking at like a technical, statistics paper, we probably want to set it really low so I just get the words like, manifold, like particular technical things that are in that, and I want to throw out any words that are not technically significant. So I tend to change them by an order of magnitude and get them as a particular result. So, yeah, one more. So if there are a lot more capital letters, so like if you're running into a lot more, if you're getting a lot more proper nouns, so that's actually what we'll show here. So that is an approximation of what we're going to try to do a little bit more accurately here. So yeah, so maybe that's a good time to jump in. So this next topic, we got really far just working with tokens by splitting our text into tokens, and you could see that we built these pipelines and we were able to approximate thematic things, narrative scope, some stylistic features of sentence length and all of this. So we can do a lot just with tokenization. So what I really want to be careful of is not to try to make it sound like I'm saying tokenizing your text and working with that is bad. A lot of times it's the right thing to do. But in this set of sequences, what I want to say is that there is something else you can do that's deeper, that relies on a lot of the advances in natural language processing in the last 10 years, or 20 years, but really in the last 5 to 10 years is where a lot of this has been developed. So just again, set up, I think this are all the same packages as before, but just if you're following along, make sure you have all of these and load them in before you follow along with the rest of the code. But yeah, I think these are the same as before. So I want to return to the clean NLP package itself. So before, we said we load in the package, we initialize a backend, we run annotators on the object, and then I combine all of the internals of that thing into a data frame. And then if you noticed, none of the other functions we used after that slide, I didn't lie, were anything to do with clean NLP. They were just dplyr and ggplot and tools that we're used to doing. Again, we wanted to do things with that data frame that we may not want to do with something that's not textual, but all the tools and functions are the same. It's the same toolbox you would use for using other text. So I just want to return to those clean NLP ones and talk about a different way of initializing different backends and getting more information about the text out that will help solve some of those problems, to do a lot of the things we were doing before, but to do them more accurately and less as sort of an ad hoc back of the envelope type thing. So in clean NLP, we currently have, this says 2 backends. We actually have 3 because we have the tokenizers one that we had before. But there are 2 backends that we can initialize that we can use inside of the package to turn our text into a normalized data set or a nice data frame. So the 2 backends that we have, other than tokenizers, is Spatie and CoreNLP. So Spatie is a newer library written very, very quickly, and I don't mean that in a negative sense. I just mean that it was built with principles and kind of the most cutting-edge stuff built in from the very beginning. It's Python library. It's built for speed and stability. It's really fantastic. It's kind of my go-to tool at the moment, and they're increasingly adding new libraries and models, and there's just a lot of development happening with Spatie. And both of these are completely open source, by the way. And then CoreNLP is an older library, older in that it existed longer ago. It's continually updated as well. It's a Java library that comes out of the Stanford NLP group, and it was probably, to my understanding, the first real working NLP annotation tool that implemented a lot of these things. The Stanford group, if you look at all of the literature, I sort of feel like every other paper in this kind of NLP pipeline type stuff came out of Stanford. They're really cutting edge. And then CoreNLP at this moment has a lot of annotation tasks, like more experimental ones than the more stable ones that are in Spatie. So that's the big difference between the 2 of them. The library that they're built in, and then one is more cutting, bleeding edge, the other one's more speed and stability. So in order to use them inside of R, it's really straightforward to do that. Inside of R, remember I said that, it's really straightforward to use them. We load in the clean NLP package. Instead of doing init underscore tokenizers, I do init underscore Spatie or init underscore CoreNLP. Much like I set the locale in tokenizers, here I have to set either the model name for Spatie or the language, the natural language, the French, English, Arabic, whatever, for CoreNLP. So I have to set which model I want to use. And then everything else is exactly the same. I run the annotators over my paths. I get an annotation object, and then I combine them into a data frame. So nothing's different other than just the backend that I'm setting up. But what is very different is the output. Well, sort of very different. So it's the same, the rows mean the same thing. So there's still tokens. So I've taken the text and I've tokenized it into its constituent parts. So I split out the words and the parts, and the words and the punctuation mark. So each row gets one of those tokens. But what's different here, although I still have an ID, an SID, a TID, a CID, spaces in the word, I have a lot more things that I learned about this text, the spaCy library or the CoreNLP library that has all of these internal models that are learned on data. We're able to learn about my text. So I have a lemma, I have part-of-speech codes, I have dependency tags, I have entity tags, I have all of these new things that I learned about them. And we're going to explain in each section of this stack of slides what each of those do and why they're useful. So the one, my go-to if you're trying to understand what's going on here is part of speech code. I feel like that's the easiest to explain. Like before we knew the tokens, now I actually know what part of speech that token is. And so the annotation task, so each of the things that adds a new column onto here is called an annotator. So it's a library inside of the package that adds a new column to the data. Sometimes these have to be done in pairs. So you can't do one annotation without the other and vice versa. But some of the common ones are tokenization. So that's the one we already saw. But the tokenization here is actually much smarter. So it's not just using essentially a pattern. It's going to figure out Mr. period is an abbreviation and not the end of a sentence. It's going to figure out Dr. period is an abbreviation and not the end of a sentence. Lemmatization, detecting sentence boundaries. Again, we could approximate that before, but this is going to do a much better job of it. It's part of speech tags, dependencies, entities, co-references, sentiment, word embeddings. So we'll talk about some of these in this deck, and then the ones we don't get to mention too, hopefully in the conclusions, we can just gesture to why these might be useful. But all of these are supported by at least one of the backends, if not both of the backends in Clean NLP. And we'll explain each of them as we go along. So just some details about these backends. So the options passed to the init functions control the models. So where I put that model in, what model is being used. The important thing, why is this so important? It's because all of these models actually have to be trained for every natural language processor. So if I use an English model on French, it'll completely fail. It won't work at all. I mean, it'll give me an output, but it'll essentially be nonsense. These are very language specific. So spaCy has support for about 4 or 5 languages at the moment. CoreNLP has about 7, but spaCy has plans to produce about 20 or 30 of them. So this is a very quickly growing space where we'll have more models and can process more and more text. And this is a benefit of the original and tokenizers one. So if you have something in a language that's maybe less common that isn't supported by these yet, if you have something in Hungarian or just a language where we don't have annotators, the tokenizers will work pretty well, but the NLP, these backends currently don't have models that work for them. So it goes even deeper than that. So not only do we need models that work for a particular language, the more complex annotator tasks, so part of speech tags are usually okay, dependencies are kind of okay. Something more complex like co-references, we actually have to train a model not just on the particular language, like English or Spanish or French, but on the formality or style of the language. So spaCy actually has a specific model that's built on newspapers to use for formal English. Then they have another one that's trained on Twitter data, if you're using Twitter data, because people use a lot of acronyms and symbols, partially because of the character limits and partially because it's fun. And they use a lot of emojis, and so it's trained slightly differently. Now, in this case, if you use the wrong annotator, it won't completely fail, but the results won't be as accurate if you use the newspaper one on Twitter and vice versa. So the downside of these, why doesn't everybody just use these? Well, partially I don't think everybody knows about them. They're pretty new. So, I mean, part of speech taggers go back a few decades, but co-reference indicators are only 4 or 5 years, so we had something that actually really gives us some good results. But the other reason that these are probably less popular is because they do require you to set up an external library. So this is the difficulty of using them. In R, it's really easy. Just 4 lines of code, no different than anything else. But the top chunk assumes that you have set up the spaCy library. So that means you need to have installed Python, you need to have installed all the spaCy modules, and you need to have installed all the spaCy models that you want to use. And the bottom one assumes that you've set up Java, you've set up RJava, you've set up all the jar files. Actually, there is a function to help you download the jar files, but you have to set up Java on your own. Depending on your platform and your experience with Java or Python, these can be a bit of a headache. On the GitHub page for CleanNLP, there are detailed instructions about them, and we're happy to talk about them either in the break or throughout the week if you want to actually run these annotators and get them working on your machine. I'd love more people to use these, and also I'd love more examples of what went wrong and how can I document that, because it works fine on my machine, so it's harder for me to figure out what's going wrong on your machine. So in the interest of time, and because I still want everyone to follow along with me, I have actually done that annotation block for the Sherlock Holmes novels that we're looking at now and the data set that we'll look at in the second half of the talk today. And I've saved them as a CSV file and put them in the GitHub repository. So you don't have to worry about the fact you don't have Python all set up and you still really want to follow along with us. Totally fine when I teach natural language processing in my intro stats, intermediate stats, and advanced stats classes, and I almost always give my students just the fully annotated text so they don't have to worry about all the backends. So that's what we'll do here. So in this slide, I'm just going to create the same metadata that I did before, just so we have the list of stories. If you'd ran it in the other one, that would be fine, but this is just to make this deck self-contained. And then I'm going to read in a CSV file that's zipped up just to make it a little bit smaller into R, and that will give me the annotated text for the Sherlock Holmes novel. So again, if you have Spatie on your machine, you can run the code that you did in the last deck of slides and just change the backend that you initialize. It's really easy, but I just know that given time and all the problems with different systems and paths and all that, that might be a headache. So you can just download the data set that's already annotated and still follow along with us. So there you go.
Come back to looking at our sentences again, but with our new method here, using the CleanNLP package. So what we can actually now do is through using Spatie and CleanNLP, it actually detects the sentence end now. So we don't have to go through this game of guessing all the possible ways a sentence might end, period, question mark, exclamation mark, etc. And this is very helpful in particular for examples like doctor or Mr. or Mrs. or SOS, right? Where every time someone uses a period, it will then read it like it was a sentence end in our other method. Rather, the pipeline and the annotator has recognized the end of a sentence. And it's not just doing that using a period or forms of punctuation. It's using the parts of speech tags and all the other components to be able to identify that at the end of the sentence. And we're going to come to part of speech tags in a minute. But it's actually sort of an iterative process through the annotator that's learning across the different methods in order to do this. And so what we can actually do here then, again, is get our sentence ends by just calling sentence end and look at it again by average across our stories. And what you'll see now is that all the sentence lengths have gotten a bit longer. So the top edge before was about 22 tokens, and now we're up to about 32 tokens as the longest sentence. So all of our sentences have actually gotten longer by doing this, which tells us that our other method was, while nice, not nearly as accurate as it could have been. We still see a general trend of the first story being shorter, them getting a little bit longer, and then them getting being a little bit more variable, but in general, the sentence lengths getting shorter toward the end. Could be stylistic, it could be a change in the genre, it could be that readers wanted less complex sentences, right? Things we can start to ask, but we might be seeing some shifts in narrative structures or ways that writing are occurring over the course of his stories, but as well as maybe over how this genre is changing as well. So just some ways that some indicators or patterns of questions that we might begin to ask as well by seeing the shift in sentence length. As well, our limitization, we're going to do this this time. So what we've added is a new colleague called the lemma. And so what this does is it takes our tokens and it converts all verbs into the same tense and all nouns into a singular case. So before, if it had been photograph and photographs, it would have read them as different tokens. But what we're doing is limitizing our text. So that means that for our nouns that will all become singular, so every instance of photographs becomes photograph. And that way, when I go to look at the top terms, top verbs, top nouns, top themes, it's accounting for that, right? Because if someone's using it, photograph and photographs, that is still a signal of them using the same idea or concept or object. As well, we're doing this for verbs. So I was walking, I walked, I walk, right? These are all versions of the same idea, right, of that. So that is one thing in which it will also be able to account for as well. It'll just make it its infinitive form. And this can be really, really important for languages. In English, this is, it's a good practice, but it's not the end of the world. For other languages, particularly, I believe it's like German, Hungarian, other languages, this is absolutely critical, where the nouns and the verbs are always changing each other depending on their form. So if you want to capture the major themes, then you need to really have these limitations, the lemmas of these words, in order to capture those because of those shifts that the language is making. And so we can actually then look here at some of our words. So we're looking at lowercase words here. And we can actually see it making that shift, the switch for us. So I's just become I. So verbs like am, is, are, was, were, be, being, been, these become their infinitive form, so is becomes be. And then that way, when we say go to summarize them or look at ways, different kinds of verb usage or different kinds of word usage, we actually have, we count them as a part of their count them sort of in their more holistic way than we were able to before. And so this helps us, again, even further with topic discovery. So we did this before, but without using the lemmas. So in some cases, new words may come up or may not. And in our case, we start to see a few different words. I believe I comes up that it did not before, and rush was not in our previous list as well. So a lot of the people are rushing or they rushed in this particular short story. So we can actually start to see some verbs come up that had not previously been before because of their different forms. And so it starts to give us a slightly different list of themes or topics that we might be beginning to see in the short story. And again, something that will really matter, again, at scale, or if people are really playing around with their terms. So I think at this point, how are we on time? You want to do part of speech quickly? And then we'll
So this is where we'll break after the part of speech tags. So this is the one that I say whenever I have to describe what is an annotator, what's an annotation, what's the natural language processing pipeline, I use part of speech tags because I just think it's the easiest to think of, before I had tokens, now I know something about those tokens I didn't know before, now I know about parts of speech. So if you think about a lot of the tricks, and I think they're tricks, I don't use that in a bad term, they're really useful tricks, but tricks for figuring out topics and characters and themes and all of those that we used with just the tokens, a lot of them actually, in some way, are trying to approximate parts of speech codes. So if we think of stop word lists and you look at the stop words in our list, most of them are punctuation marks, pronouns, conjunctions, interjections, determinants, and verbs. Common verbs. So in stop words lists, in some ways, to me, it's actually really just trying to get rid of those parts of the language that are fixed, that we call them function words in linguistics. So punctuation marks, we can make up new nouns and new adjectives, and people do all the time, especially with nouns. We don't typically make new punctuation marks or new pronouns. They don't come up very often. So stop word list is really filtering out those types of parts of speech that don't contribute thematically to what's going on in the text. The checking for uppercase marks, that was really, as we were actually calling it this, we were really looking for proper nouns, trying to figure out not just nouns, but proper nouns, and distinguishing them from non-proper nouns in the text. And we were using that by figuring out, what words are capitalized, and that works roughly well, but having proper parts of speech tags would be better. In the frequency table, where we're looking deeper down into the frequency table, it's actually doing more than just this, but when you think about what's in the frequency table, like the top of the frequency table that aren't stop words, tend to be just really common verbs. and adjectives. So using part-of-speech tags, we'll be able to do a lot of the things that we did on the first with just the tokens more accurately, and we'll also be able to do a lot more that we couldn't do without them. So I'll just show some examples of them. So part-of-speech code, so what are the parts of speech? So if you had to learn them in primary or secondary school like I did, and like I know Lauren did, you probably learned about parts of speech like nouns, verbs, adjectives, adverbs, maybe determinants. I think there was some fun song about all of them that I forget now. So linguists actually think of parts of speech as being much more granular than this. And they don't agree on what the part of speech categories are. They do agree that they differ language to language. They change over time even, but they sort of think that it's much more granular than the ones that we think of colloquially for parts of speech. But there are different sets of them. But a commonly used one, or at least the one that most linguists start with and then will add or subtract their own from, are the Penn tree bank codes. And so Spassy and the Core NLP use a modified version of the Penn tree bank codes. So they look like this. So there are 48 parts of speech. So they distinguish between adjectives, comparative adjectives, and superlative adjectives, or there are 7 different types of verbs. There are cardinal numbers, there are ordinal numbers, so much more granular than the way that we would have thought of them. But this becomes very useful if you're a linguist and you want to understand how words are used in the language. And these are the Penn tree bank codes for English. There are Penn tree bank codes for other languages as well. And there's not a one-to-one correspondence. At the same time, so I'm sort of telling you, what you think of as a part of speech is different than what linguists think of them as. But at the same time, there's a movement to construct something that more closely resembles what we're all taught in primary or secondary school about parts of speech. And so these are called universal parts of speech. And the goal is to construct a set of parts of speech that are somehow universal across all languages. So obviously, these are made mostly by people who speak Western languages and study Western languages, but they do map pretty well onto most languages. They've even found mappings from part of speech codes that were developed for like Navajo, which is a very different language than most of the others that exist in the world today, and mapping them into this set. So this set is fairly universal, and they conveniently map onto what we colloquially think of as the parts of speech, so verbs and nouns and adjectives. So in the output of the clean NLP, we actually have 2 columns. So we have a part of speech column that gives a granular term, which currently is the Penn tree bank code. And then we have a UPOS, which is the universal part of speech code. So we have both of them. And in our work, we tend to use actually both of them. Sometimes we want the granular ones, sometimes we want the less granular ones. And we sort of go back and forth depending on the application. Okay. So if we actually go through and look at what these are, you can see that there are 4 different types of nouns. So this is something I make my students do. There's an NN noun, an NNS noun, an NNP noun, and an NNPS noun. And so if you look at examples of them, you can see pretty quickly that the NN are singular nouns, NNS are plural nouns. I always forget if the S stands for singular or if it's like adding S to the end of something, but those are the plural nouns. NNP are proper nouns, and NNPS are the proper plural nouns. They're much more rare than the other 3. And similarly, I just encourage you to go back and look at the Penn tree bank and try to understand, like, what's the difference between these 4 types of adverbs? Because reading the description doesn't make it so much sense. But if you want to understand what these mean, I suggest just taking the data frame and filtering by the part of speech and looking at some examples. So let's actually use this to do something we had done before a little bit more accurately. So I'm going to take my data set that comes out of the annotation object. I'm going to filter it where just the universal part of speech is equal to the proper noun, so prop n. And I'm going to count by ID, by story, and by the word, and figure out what are the most common words, and select just the top 10 most frequent proper nouns, join it into the metadata, and look at them. So this is what we did before, except instead of having this hack where I'm trying to figure out, is this capitalized or not, I'm going to use this model that was trained on a large corpus and is much more accurate and nuanced than that to figure out what the proper nouns are. So you'll see for the most part this doesn't change much because our hack worked pretty well, but as someone had mentioned, sometimes that's not the case. this would actually fix that. This would find the proper nouns. The one thing that does come in here that we did not have before is Mr., so the honorific Mr. period. And this is where you can begin to see that the tokenization here is much better. Mr. MR period is one token, as it should be, rather than Mr. MR and then the period being its own token. It's really, linguistically, we think of it as one token because it's an abbreviation. And then I'll end. Oh yeah, this will be perfect. So one thing that we can do, and I want to show you this partially because I'm going to show you a different way of doing the same thing after the break. But I want to show you how we can do it without any external libraries by just putting together more and more complex chains of piping commands. Because we tried to keep the piping commands that we were using in the seminar relatively straightforward. But I did want to say that when I'm doing text analysis, they often get much more complex. So just wanted to show an example of one of those where we can put compound words back together using the data that comes out of the NLP pipeline. So if you notice something about this list here, one of the main characters is Irene Adler. But Irene and Adler here are treated as separate tokens, as they should be. They were tokenized into two different words. But if I wanted to create an algorithm that spit out, you put in a story and it spits out what the most important characters are, I probably wouldn't want to say one character is Irene and one character is Adler. I'd want to put them together and say there's a character named Irene Adler, there's a character named Sherlock Holmes. And so the way to do that is I can do that by mixing some mutations and summaries over the data and just figuring out when do two or more proper nouns follow one another. So if there are two proper nouns with nothing in between them other than spaces, no commas, no verbs, no adjectives, then that would be a compound noun. There's no other way that two nouns would be right next to one another like that. So this is essentially doing a mutation, and it's figuring out, did the one that came right before it, is that TID equal to the TID of the one after it? So when we summarize that all up and figure out the most important compound words, we get the characters that we would actually expect. So Sherlock Holmes, Irene Adler again. Because I didn't take the unique ones, but Irene Adler. We get not just characters, but we get compound words like Baker Street and Norton Street is later down the list. And so we see these compound words that come together. So I wanted to show this because after the break, we'll talk about named entity recognition and dependency trees. And they are a way of doing this, going even one step further and deeper to do it again. But I wanted to show how you could do this just with the part of speech tags. So how are we on time? Okay, cool. So I guess we'll break there. We at? Yeah. Oh, yeah. Yeah, and then we'll come back at, what is it, 3? 4. I don't know what time it is. Yes. 4. At 4. And we'll finish this deck and then do some modeling of our data.